Hey, we got a really fun problem and something of particular interest for myself. This having to do with more particle physics applications. Our statement reads a circularly symmetric magnetic field, B depends only on the distance from the axis, pointing perpendicular to the page, occupies the shaded region in the diagram. If the total flux, which is the area integral of B is 0, show that a charged particle that starts out at the center will emerge from the field on a radial path, provided that it escapes at all, because there is energy involved. On the reverse trajectory, a particle fired at the center from an outside will hit its target if it has enough energy, though it may follow a weird route getting there. All right, let's look at what we're talking about. We see that we have a field region, the particle trajectory, and this is what we expect in the circularly symmetric field. All right, so let's dive through it through the lens of angular momentum. So we know that the angular momentum is acquired by the particle as it moves from the center to the edge, and that we can find this via taking the time derivative and integrating. We know that dl dt is equal to the normal derivative, or the normal vector rather. So from there we know that that's equal to r cross f, and we know what f is, which incorporates the field via the Lorentz force. And we just keep pushing those things down, keep pushing them down. We see that v can be equal to dl dt, and the dt's cancel. So that's why we take the q outside and we end up with the dl right there. And then from there, we just apply the some product rules for the double product. And we see that we end up with this dot product scenario here. And we can rationalize what these things will equal because R is perpendicular to B, so their dot product must equal 0. And we know that R dot dl is equal to R dot dr in this case, so we just pass through that. We know that we can set this up in terms of 1 over 2 pi times 2 pi r dr, which we'll see why we want that set up in a second. So when we plug these in, we end up with this, okay? And what's cool about this setup is that putting it in terms of 2 pi r dr allows us to rewrite this in terms of dA, which instead of just a linear integral, a line integral to dA. And thus, when comparing these two things, we can see that L is equal to negative Q over 2 pi capital Phi, where Phi is the flux. Okay, so we know that those two things are proportional, as we just said. So if the flux is 0, then L is 0. And the charge emerges with 0 angular momentum, which means it goes along the radial line. So that's pretty cool.